Hello everyone, this is Dr. Daya Sagar Chowdary, Senapati, Assistant Professor, Department of Electronics and Communication Engineering, Aditya University, Surampalem. Today I would like to discuss about the topic D flip-flop. So coming to the learning outcome, at the end of this lecture, student will be able to understand, analyze and design sequential circuits using D flip-flops for data storage and synchronization. Coming to the types of flip-flops, we already discussed previously about the SR flip-flop, that is set reset flip-flop. Now we discuss about the D flip-flop. We simply call that one as a data flip-flop. So coming to D flip-flop, a D flip-flop is modified form or modified version of SR flip-flop. In SR flip-flop, when R is equal to 0, S is equal to 0 or R is equal to 1, S is equal to 1, the outputs Q and Q bar either don't change or they are indeterminate. That means if we consider the last row, so both S is 1, R is equal to 1, so the output is nothing but whatever the next state Qn plus 1 is nothing but the invalid state. So in order to determine the other ways, we have to calculate other flip-flops also. We will go to the other flip-flops. Right now we are simply maintaining the two inputs, like previously we are using 0 and 0 or 1 and 1. So 0 and 0 there is no problem, but 1 and 1, so there is invalid condition in SR. Now what we will do is, so one of the input is high, so we are giving the other input as, so here 1 and 0, that means one is high and other is low, or one is here, this is high or this is low. So likewise we are simply connecting these S and R terminals to one terminal. One terminal is directly connected, the other one is inverted. That means with the help of one inverter, we are connecting this terminal. So finally we will get only one terminal. So whatever the input D is connected to this terminal, so now the entire flip-flop acts as a D flip-flop. The outputs are Qn and Qn bar. So simply we call this one as a previous state or present state or next state. So we can call this Qn and Qn bar, or Qn, this is nothing but the opposite, that is inverted Qn, Qn bar. So this is quite inverted Qn bar. So coming to the D flip-flop, a D flip-flop is an electronic device also known as a data flip-flop or a delay flip-flop. So both we can call, and use it to store a single bit of data, because each flip-flop can store a single bit of data, either it is 1 or 0. It operates based on a clock signal and is primarily used in synchronous circuits. So before mentioning this one, synchronous circuits means definitely it is having one clock signal, and if we connect two or more, like multiple flip-flops, so depending on a single clock, we call that all the flops are in synchronization. So this is the term. So that means, so all the D flip-flops that are connected to a single clock signal, we call that all D flip-flops are in synchronous. So we most of the time we are using this D flip-flops in synchronous circuits. This is the simple block diagram. That means a block diagram contains the data input. So we already previously mentioned that D is nothing but the data, that is D input, and we can expect the output, that is data output. So this is the clock terminal, and that too, this is a clock pulse. We call this one as a pulse. That means it is maintaining certain frequency. So that means it is having some time period. We know that is f is equal to 1 by t. That means it is maintaining certain frequency, and that too here it is mentioned, this symbol means that is clock edge. Either it may be positive edge, pause edge, we call simply pause edge, or neg edge, that means negative edge. That means this symbol indicates that is the edge triggered. So this is the edge triggered. So if it is edge triggered, we call that one as the flip-flops. Now this is the D flip-flop, and coming to the characteristic table. So this is a characteristic table, and simply we call that one as a truth table, or while coming to this flip-flops, we call this one as a characteristics table. Now if we observe that this clock signal, that is 0, if clock signal is 0, irrespective of inputs, the outputs are no change. We call that one as a no change, means present state which is the previous state. That means memory, there is no change. We call that one as a memory line, that is no change. Now coming to the clock is high. When clock is high, simply the Q, whatever the output Q is following the input, that is D. That means Q follows the D. simply we can mention Q, that is follows the D when clock signal is high, that is clock signal is 1. So likewise, if we check the characteristic table, so if the D is 0, the output whatever the Q is 0, and D is 1, the Q is 1 only when the clock signal is high. That means we can use this again Q is equal to 0, Q is equal to 1, that is reset and set. So because of we are taking this D flip flop, before that, that is SR flip flop. So the same whatever the outputs, that is reset condition and set condition, we are taking. So that is why here this is mentioned in this particular column. So this is the characteristic table for D flip flop. So whatever the D is there, if clock signal is high, Q is equal to D. Now coming to the cases, so if we observe that case 1, so when clock signal is 0, so flip flop does not respond to input D. So does not input respond D, that means simply the output follows the previous state. Q retains its previous value, that means holds state, that means simply it is acting like the whatever the previous state. If previous state is 1, it is simply following the previous state, that is 1. If it is the previous state is 0, that means simply it is following the output 0. Now case 2, so when clock signal is high and D is equal to 0, then the output becomes Q. Q is nothing but our output, that is 0. If Q is 0, so Q bar we know already, Q bar is quite opposite, that is 1. Now case 3, so if we come to case 3, so when clock signal is high, again clock signal is high and D is equal to 1, our Q, output Q becomes, that is also 1, and as usual Q bar is equal to 0. So this is the simple characteristic table that is explained through sentences. Now if we observe, this is a D flip flop circuit diagram. So it contains, if we observe the dotted line, which is nothing but our SR flip flop, so SR gated flip flop, because the gate whatever the clock signal is directly connected to the clock terminal of the SR flip flop, and finally data, we call that one as a D input or data input, that is connected directly to S terminal and invertly connected to R terminal. That means we are using simply one inverter here and that is connected to R terminal. Now this is acts as a complete D flip flop. Sometimes people will ask like, so the entire circuit is developed with the help of entirely NAND circuits. That means because NAND is a universal gate. So in that case, this inverter is also replaced with the NAND gate. That means NAND gate contains two input terminals. Those two input terminals are again directly connected to a single terminal. Now the NAND gate, whatever the NAND gate, that is directly acts as a inverter gate. So if it is inverter gate, again there is no change in the entire circuit and the final circuit is like this. That means we are simply changing our inverter gate to NAND gate. Now this is again the truth table whatever we are observing, and if these are the key points we observed, so that means we can observe these two key points, that is the output Q follows D only when the clock signal is active. That means clock signal is high, Q is equal to D, simple, and otherwise it stores the previous value. So previous value is there. If it is 0, the clock signal is 0, then simply the output Q follows the previous value. Whatever the D is there, it simply follows Q is equal to D. That is the excitation table or some characteristic table. Now this is the characteristic table again I have given here. Now if we want to characteristic equation, so directly we can use the K-map. So K-map means again it contains two inputs. So two inputs means there are four combinations here. So for four combinations we can construct four boxes with the help of K-map. Now 0 0 0 1 1 0 1 1. So these represents four boxes. Now according to the Qn plus 1, that is next state, so we have to identify the ones here. So these two particular ones we have to identify the corresponding inputs 1 0 and 1 1. So in place of 1 0 we have to place 1 here, in place of 1 1 we have to place here, because this is 0 0 box, this is 0 0 box, this is 0 1 box, this is, and 1 0 box, this is 2, 1 1 box, that is a 3. This is the representation, this is 1 1 box, that is 3. So likewise we construct this K-map, and with the help of this K-map we can simply identify the equation. So if we observe the Qn plus 1, because Qn plus 1 is the output, so Qn plus 1 is the output, we are giving the K-map for this Qn plus 1. Simply if we group these two ones we will get the irrespective of Qn, the Qn plus 1 is directly following the D. If we observe this one, that means the output follows the input when the clock signal is high. This is the key point for this D flip-flop, and that is why we have given that Qn plus 1 is equal to D of n. So this is the characteristic equation for this particular D flip-flop. Now coming to the advantages, eliminates invalid state. So previously we observed that in SR flip-flop 2 ones we get the invalid condition. So simply it eliminates the invalid condition. So D flip-flop eliminates the invalid condition. Unlike SR flip-flops, it avoids the undefined condition whatever we mentioned, that is S is equal to 1 and R is equal to 1 condition. Now this is a simple operation because only one input, that is D, making it easy to design and understand. So simple operation and simple circuit. Coming to reliable data storage. So as we know already, each flip-flop can store one bit of data, either it may be 0 or 1. So here the stores data accurately when the clock signal is high. That means here the clock edges, we call that one as a clock triggered. Maybe the clock triggered is negative edge or positive edge. We call simply pos edge or neg edge. So we can save the data either 1 or 0. That means a single bit we can store. And widely used in synchronous circuits, that means we already discussed that synchronous circuits means all the D flip-flops that are connected to a single clock signal, we call that one as a synchronous circuit. And prevents race condition. So there is no race condition here, that is why controlled by clock signal reducing, that means timing issues also reduced here. Coming to the disadvantage, so requires clock signal. So definitely only one input signal, that is D, is there. Other input terminal, we call that one as a clock signal. So definitely it requires the clock signal, and entire circuit depends on the clock signal only and cannot operate without a clock signal. That is what we have mentioned. And propagation delay. So output changes slightly after clock edge. That means not instantaneous, because each and every gate contains some delays. If we observe in tools, either each gate contains 1 nanosecond delay. So definitely that delay after that means if we apply input, definitely we will get the output after this 1 nanosecond delay. That means gate delay we have to calculate. So likewise, this is also one of the disadvantages. And power consumption. So continuous clocking leads to higher power usage. So definitely clock signal must be there, and clock signal, if clock signal is there, definitely the clock signal draws the power from the battery. So that is why power consumption is more. And coming to not suitable for asynchronous systems, that means we already discussed it. These D flip-flops most of the time we used in synchronous circuits. And coming to applications, used in registers, shift registers. So used in registers means for particularly most of the time we have to store the data. For that reason we are using these D flip-flops in the registers. And coming to shift registers, most of the time we have to shift the data, that either it may be 4-bit data, 8-bit data, 16-bit data according to the requirement of the processors or RAM or ROM. So there we have to use these D flip-flops in order to store, and at the same time we have to shift this data. And either counters also we have to use this D flip-flops, because we need to store the data, because we need to count and we need to store the data. For that reason most of the time these D flip-flops are used in counters. And memory elements, because it is having naturally stores the data, that is why used in memory elements like that RAMs and sequential circuits. And data synchronization, so synchronizes data between different clock domains. And pipeline circuits means most of the time we used these circuits in VLSI designs. So widely used in pipelined architectures for timing control. So in order to maintain our timings and reduce the timings and reduce the time delays, most of the time we used these circuits, these flip-flops. And frequency divider circuits in D flip-flops also used for divided by 2 circuit and divided by 4 circuit, divided by 8 circuit, divided by 16. Likewise, we are using this D flip-flop because this is for to generate the clock signal, the frequency dividing circuit. Most of the time we will get the only single signal from the PLL, phase locked loop. So in order to supply to all the internal devices, we need to give this single clock signal. That means coming from the PLL, single clock signal given to all the other signals, that means other devices by using this divided by 2 circuit and divided by 4 circuit and divided by 8 circuit divided by 16 circuit. Example, Bluetooth consumes one type of frequency and Wi-Fi consumes one type of frequency, but we are using only PLL, the single PLL we are used in the most of the electronic gadgets. So that is why this is mostly used in the frequency divider circuit. That means D flip-flop is used as a frequency divider circuit. And coming to the summary, so the D flip-flop is a fundamental building block in digital electronics used for data storage and synchronization. It captures the input data at a clock signal or clock edge and holds it until the next clock cycle. Due to its simplicity, reliability and elimination of invalid states, it is widely used in registers, memory units and modern VLSI systems. However, it depends on a clock signal and introduces slight delays which must be considered in high-speed designs. Thank you.